Great. Good evening, everyone. Thank you so much for joining us tonight. My name is Bree Rossiter, and I am the Conservation Program Manager for the Lake Winnipesaukee Alliance. For those of you that may not know, the Lake Winnipesaukee Alliance is the leading nonprofit helping to protect Lake Winnipesaukee and its watershed now for future generations. We do this a variety of ways through water quality monitoring, through watershed management plans, through restoration projects, and through education and outreach, like this webinar tonight. A few housekeeping tips before we get started. If you could please stay muted during the duration of the presentation, just to limit any background noise. You are welcome to type your chats in or your questions into the chat absolutely anytime during the presentation. And we will have a Q&A session following Rebecca's presentation. And this recording will be posted to our YouTube page if for some reason you need to leave early. With that, I would like to take a moment to introduce our presenter. This is Rebecca LeCain. She is a Geoscience Specialist with the New Hampshire Geological Survey. She heads public outreach and data preservation programs. She assists with geologic mapping and groundwater projects. She earned a master's degree in geology with a concentration in environmental paleontology from UNH. And her fun fact is that she is perpetually upset that New Hampshire does not have more fossils. So we are really excited for tonight's presentation, and thank you so much, Rebecca, for being here. With that, I would love to turn it over to you to begin the presentation.
All right. Thank you so much for having me. All right, let me start sharing. And I'll go to my notes for a moment. There we go. All right. Can you see the title screen?
Yes, all set.
Okay, great. All right. So as Bree was saying, I'm Rebecca LeCain. I'll be talking about the geology of many of the lakes here in New Hampshire, and I'm with the New Hampshire Geological Survey, which is part of the Department of Environmental Services. And the survey has a number of key projects that Bree was mentioning. Probably our biggest one is doing geologic mapping. Uh, and we are working on mapping the entire state to a useful scale with both bedrock and surficial geology in mind. And I'll go over the differences in these a little later in the talk. We are also involved in groundwater well monitoring, which means that we check a number of wells all over the state for how the aquifers that they tap into respond to precipitation. And you may have heard recently that most of New Hampshire has been in moderate drought, and we're one of the agencies involved in determining that. Also tied into groundwater, we house the water well inventory. So every time a well is drilled in the state, the drilling company sends us the general information for that well, and we digitize and keep the records. So we use those records to help determine how thick the surficial sediment is above the bedrock. The survey also works with water above ground. We're a key group in the stream crossing assessment. So everywhere a road crosses a stream in the state and a culvert or a bridge was put in, we have a record for that. And we've been assessing whether those culverts are damaged or undersized or have other issues so that towns can better prepare for replacing those culverts or see where there's potential for flooding. And I assist with all of those projects, but as Bree was saying, my main focuses are outreach. And I had read Bree's article a few months ago about the geology of the Lake Winnipesaukee area, and I reached out to her because I'm always happy to see people communicating good earth science. And she asked if I would come and speak with you and explain things in a little bit more detail. And then my other focus is running our data preservation initiatives. And the survey has thousands of maps and paper documents, including a couple of copies of the first geologic survey of New Hampshire, which is the actual literal survey of the state's resources that was originally conducted in the late 1830s. And we were one of the first geologic surveys in the country. So, as you may imagine, over the years, we have a lot of papers and documents. And it's my job to inventory those physical resources and preserve them, and often to digitize them and make them more accessible to everyone so they're not just sitting on our shelves in our storage areas. All right, because I'm going to go over quite a bit of information, I wanted to give you kind of an outline of what I'm going to be talking about. So I'll go over some general geologic concepts and terms, some of the basic, really fast geologic history of New England, some of the bedrock of the Lake Winnipesaukee area, how glacial lakes form in general, how scientists know about glacial lakes, and then some of the history of Winnipesaukee itself. And I'll also have a couple of quiz questions for you to answer in the chat. So, to make sure you're paying attention. All right, so just to give some basic information so you can understand some of the terms I'm going to use. The basis of all of geology is the rock cycle, and there are three main types of rock. There's sedimentary, metamorphic, and igneous. So every rock you have ever seen or will ever see, including rocks from space, are at least one of these three types. So sedimentary rocks form from other types of rocks being broken into pieces by erosion, and they pile up and are cemented into stone. They often have layers and may contain fossils. Metamorphic rocks are any type of rock that gets squished and heated enough to change composition, but not to melt. They tend to look wavy and are sometimes shiny in certain directions if you hold them the right way. And then igneous rocks are any type of rock that was heated enough to melt, and then they got cooled back down again, and they frequently look spotted when seen up close. And what drives this rock cycle is plate tectonics. So the Earth's surface is made up of different pieces, and because those pieces sort of float on top of the mantle, it's a plastic basically, and the mantle is moving around, then the plates move around too, and they bump into each other. When they slide past each other, it causes earthquakes. When one goes underneath another, it can cause mountains and volcanoes. And then when they pull back apart, then it causes areas of rifting and outpourings of lava. And so right now, New Hampshire is sort of towards the eastern middle of the North American plate. And so, since we're not near a plate boundary, New Hampshire is fairly geologically stable right now. It didn't used to be that way. With plate tectonics and the rock cycle in mind, I'll start getting into the geology, the bedrock geology of New Hampshire. And this picture gives a general idea of how the continents fitted together about 550 million years ago, the late Proterozoic era, but it has modern state lines to kind of show you where things are. So New Hampshire would have been here. And as you can see, if we'd been around at this time, we wouldn't have been on land. We would have been at the bottom of a shallow ocean shelf that was just off the edge of the continent that we call Laurentia. As Laurentia and Gondwana were pulling apart because of plate tectonics, the then the ocean water came in, and all of the sediment that was eroding off of Laurentia was pouring into that ocean. And it was eroding fairly quickly, especially by modern standards, because there weren't any plants on land to stop the erosion. It was mostly bare rock. So there were thick layers of sand and clay in that ocean. And as these layers got thicker, they cemented together and hardened into sandstones and shales and limestones. And then came hundreds of millions of years of plate movements as the continents moved slightly apart and then slowly came back together. And this whole diagram is sort of what that would have looked like, kind of from the side. And there were several of what we call island arcs, which are pieces of continental crust that all smashed into Laurentia. So they were all kind of moving into each other. And all of the older seafloor rocks got squished together, which leads us to your first question. All right, so question one, and like I said, you can type the answer in chat. So the sediments that had been on the ocean floor got mashed together at really high pressures by these island arcs and continents smashing together. So what type of rock would this have formed? Is it A, igneous, B, metamorphic, or C, sedimentary?
And if anybody needs to know how to get into the chat, you can unmute yourself or uh,
That's
happy to help. There's a button on the bottom of your screen. Anybody have any guesses? We
C.
have a C.
Good guess. I think there we go. So,
One
and
C and two B's. I don't know if you can see that or not, Rebecca, or if it's
all
easy.
right, I
Three
just
B's.
popped out of it. All right. So the bees have it. It's metamorphic. So it was originally sedimentary. So the shales, limestones, all those things were sedimentary rocks. And then because they got smashed together, they were metamorphosed into other rocks. All right. So they're called metasedimentary rocks now, if a geologist wants to be more precise. So all of this mashing was going on. There were also several intrusions of magma, shown by the little orange and red blobs. And if these cooled underground, then they became granites and related intrusive igneous rocks, though many of them vented at the surface to form volcanoes. And yes, there used to be volcanoes in New Hampshire. As you can see in the bottom right diagram, about 270 million years ago, the land masses had collided again to form the supercontinent Pangaea, and which is the supercontinent that most people have heard of. But just be aware, it has happened a few times in Earth's history that all of the land masses mashed together to make basically one big land area. And this is about what this part of Pangaea would have looked like at that point. So New Hampshire is right in here, and it would have been very near the equator, which is this white line. And so the climate would have been much warmer than today. We would have had all kinds of tropical plants and animals, although they would have looked quite a bit different from the plants and animals that are at the equator now. And New Hampshire was crushed into what is now Northern Africa and Western Europe. So some of the rocks, kind of the easiest place to see this is out at Odiorn State Park, out at the coast. There are some rocks there that their sister rocks, rocks that are most closely related to them, are over in northwestern Africa. So through UNH, that's a field trip that they always take the geology students on, is to go see these rocks. And after everything had smashed all together, then there was likely a super plume of upwelling magma that started to force the plates back apart. And they continued to separate, and they do that at about the speed that your fingernails grow. So it's a very, very slow process, but given hundreds of millions of years, then it moves a lot and can shift quite a bit. And so the Atlantic Ocean formed. The plates separating also led to more volcanism and the formation of the Southern White Mountains and several calderas that we now see as circles of igneous rocks on the bedrock map of the state. So here is the bedrock map of the whole state, and you'll see that there's a general northeast southwest trend to those metamorphic rocks that we were talking about earlier. And those are those ancient seafloor rocks that got squished by all the island arcs and continents smashing into them and wrinkling everything. It's a bit like if you slide a rug from one end, you try to just push on a corner of the rug, then it just makes a bunch of wrinkles in it. So all of this rock got wrinkled and folded in a lot of ways. And the background photo, you can see one of these big folds in a metamorphic rock. And then just here's some granite, as always looks nice. And then there are also these blobs of yellow. And those are the much more recent calderas that rising magma, as it was coming up through the crust, created these rings, and I'll discuss that in a little bit. But that rising magma also pushed up those old metamorphic rocks. And the kind of interesting thing is that the northern White Mountains, which are actually these green and pink and blue map units up here, those aren't igneous rock like granite, like the southern White Mountains. Those are old metamorphic rock that were pushed up and then were resistant to erosion, and so they're higher than these younger rocks. And a fun fact is that we're not called the granite state because most of the bedrock is granite. We're actually called that because we had good granite for building and statues. And in the 1800s, New Hampshire quarried and shipped that rock all over. And so people recognized New Hampshire granite as being of good quality. We still ship quite a bit of granite, Concord granite and Conway granite all over the world. And there was a song made about New Hampshire in the early 1820s that the songwriter mentions us as the granite state. And so that was several years before there was a geologic survey to see what kinds of rocks even existed here. So it was just because we had good granite. So that's a very quick overview of how most of the rocks in the state got to where they are now. And so let me kind of shift focus in on the Winnipesaukee area specifically. And on the state map, Lake Winnipesaukee is kind of in this area. So this is our bedrock map of the Winnipesaukee Quadrangle. And the oldest rock in this map is the metamorphic schist, those seafloor rocks that had gotten smashed together. And on the map, it's this blue map unit in the bottom left-hand corner. And then the yellow map unit, this diorite, intruded into that quite a bit later. And that's the diorite. We've drilled wells around Lake Winnipesaukee, and you see that in quite a bit of the area. And then hundreds of millions of years later, the syenite intruded both of them as part of the Belknap ring dike. And these blobs of rock here, you can kind of see her in the circular pattern. And there's Rattlesnake Island, and I think the little one is Diamond Island, but you can see are part of this big circular complex. And that originally would have looked something kind of like this, a big ring at the surface of volcanic activity. And what's going on below the surface is this. And this diagram is actually for the Belknap Mountains specifically, but the general shape is pretty applicable to other ring dikes. So I'll go through that real quick. So A is a little bit simplistic. Most of these older rocks that were here had, they were those metamorphic seafloor rocks. They had faulted and been eroded for hundreds of millions of years, so they would have looked a lot more chaotic than this. But they weren't really the point of this image, so the author left them pretty simple. B and C show a couple of different pulses of magma as it welled up to the surface in these rings and formed the caldera shape. And this all started in the mid-Jurassic, around 170 million years ago or so. And then D represents the magma chamber itself rising up through the rock. And you can see it didn't come to the surface. The magma chamber itself didn't make it to the surface. And magma rises for the same reason that hot air rises. The hot magma is less dense and has more water in it than the cold rock that's around it, and it moves towards equilibrium as best as it can, and it melts and warps the host rock as it goes. Uh, and then figure E is the final stage of this volcano. So think something that looked like the ring dike in the picture in the background here, or like the Crater Lake area in Oregon. And then in between E and F is the modern Belknap Mountains. F is over 100 million years of erosion. So there's a really long time where all of this ground surface was eroded away. So what we're left today in the Belknap Mountains is just the smallest bit of the inside of the roots of the volcano that once would have been here. So this is the same thing for the Belknap Range, the Ossipes, which are a little bit younger, the Southern White Mountains, and all of the other volcanics from this series they're not the cones of the volcanoes like we would see on an active volcano today. They're the remnants of what would have been deep beneath the ground at the time that the volcanoes were erupting. Uh, and a big reason for a lot of the erosion, much more recently in time, were the ice sheets. We made it to the glacial part of this talk. There were several glaciations, but this map is technically one of the older ones, so from the Pleistocene, about 1 million years ago. Uh, but the most recent ice sheet is called the Laurentide ice sheet, and it would have looked very similar to this. And in New Hampshire, right in here, it would have been about a mile thick. So if we had been around 20,000 years ago in this area, we would have been smushed under tons of ice. And above the ice, it would have looked a lot like this photo of Greenland in the back. And that much ice bulldozes the land completely. So it smoothed over mountains. There is evidence that it went over Mount Washington. So that's how thick this ice got. And it carved big glacial valleys like Franconia and Crawford Notches. It carried huge boulders and tons of gravel and sand all over the place. And as it started melting, it also left huge lakes, bigger than Winnipesaukee, and stream channels and a bunch of other landforms. So just as a side note, I'll probably use ice sheet and glacial and glacier kind of interchangeably, but technically they are distinct terms. An ice sheet covers a huge area and goes over mountain ranges, whereas glacier usually refers to mountain glaciers. So they're also moving ice, but that ice stays within the valley in the mountains. Glacial processes are things that happen because of moving ice, so can refer to either type of ice sheets or glaciers. And the ice moving is the key thing. Uh, It moves because it gets so big and heavy that it starts flowing internally due to gravity. And if it stops moving, then it's dead ice and is no longer a glacier. As I said, as the ice sheets melted, they formed huge lakes. The largest ones around New Hampshire were Glacial Lake Hitchcock, which is the Connecticut River Valley. So as you can see, extended from uh, very southern part of Canada and northern Vermont all the way through Massachusetts and Connecticut, and drained into the ocean, out through the New Britain Spillway and through Connecticut. So as you can see, this was a remarkably large lake. The other big one was the Merrimack Lake, Glacial Lake Merrimack, where the Merrimack River is now, but as you can see, much, much larger. Most of Concord and Manchester and Nashua would have been underwater at this time. And then these black lines across the extent of the ice sheet they're the extent of the ice sheet at different times. So as it retreated northward, these are kind of where we can tell the ice sheet was. And so, just an interesting fun fact, Cape Cod is almost entirely made of sediments and boulders that came off of the ice as it met the ocean there. And so there would have been a lobe of ice here at Cape Cod for quite a while. And so there's no bedrock. Like if you dig a hole in Cape Cod, you're just digging into till glacial sediments that this ice sheet um, put off. And so the sheer amount of material that much ice can move is absolutely staggering. All right. And so how and why did these huge lakes form after the glaciers started melting? This is a really great diagram that shows the various stages of this. I realize it's really dense. Um, the panels on the left are a side view, and the right is these same time, but looking from the top down. And so I'll break this image up a little bit because I realize there's a lot here. Panel 1 represents the greatest extent of the ice. And ice sheets are like huge conveyor belts. The ice continually moves forward internally, even as the ice front retreats backwards. So this is kind of sometimes a difficult thing to picture in your head, but think of a conveyor belt that only moves in one direction. So even if you shorten the conveyor belt, it still moves things that are in it in the same direction, even as the conveyor belt itself gets shorter. So the ice sheet, it doesn't actually retreat in that it doesn't, turn around and start moving backwards. It's still dumping stuff in the same direction at the end of it. It's just that the end moves back northwards. Right. So ice sheets dump huge amounts of sediment that are trapped within the ice and under the ice and on top of the ice. And when they dump sediment at the end of them, it's called, well, all of the sediment is called till, and it's dropped everywhere, but especially at the toe end of the ice, it forms a terminal moraine, which is a ridge of sand and cobbles and boulders. They also gouge out some of the rock underneath. They shave off hillsides, and the water flowing underneath the ice carves channels into the sediment and rock as well. So, as you may imagine, these processes take advantage of the topography of the land that was there before the ice. So, if there were rivers and valleys before the ice, then the ice makes them deeper, and the ice will be thicker where there were deep valleys. And then areas that were higher, like mountain peaks and hills, would get eroded away more quickly. All right.
Rebecca, I do have two questions if this
Oh,
is a
yeah.
good point before we move on. Alan asked Red Hill syenite in regards to that slide.
So the Red Hill um, is a slightly different area. I believe we have information about the Red Hill Boulder Train, and um, I'm not, it's been a little while since I've looked into it. So I would have to figure out what some of that is. Um, but yeah, we do have information on the Red Hill area.
Great. And then second question is Long Island also Lake Cape Cod, i.e. no bedrock, or is it a terminal moraine?
I believe Long Island is a bit of a mix. I think that there was some land there. Um, I can go back to this slide, but a lot of it is also glacial till. In the meantime, some of this has gotten eroded away. Um, but yeah, I'm pretty sure Long Island is a bit of both.
Great, thank you.
Mhm. So panel two here. The ice has started retreating a little bit as climate changes. It's still relatively cold, so there's not a lot of liquid water around except in the warmest parts of the summers. Uh, but what happens for these to start retreating is there's less snow accumulating up at the top of the glacier, and the toe of the glacier melts more during the summer months. So it still deposits a lot of sediment and also chunks of ice, which are kind of like icebergs, but sitting on land instead of water. And then once the ice melts, then these chunks of ice, the sediment formed left around them, and so they form kettle holes that often have ponds in them because they're depressions that have no inlet or outlet. And in panel two on the right, you can also see that the stage leaves what's called hummocky terrain that is chaotic and lumpy. And we can see different types of terrain on LiDAR, and I'll talk about LiDAR more in a little bit. But we can see these textures and often figure out what kinds of sediments are there before we even get out into the field to check. Panels 3 and 4 show the ice melting more quickly. There can be huge amounts of water coming off of these ice sheets, and the water tends to pond between the moraine and the ice. So you'll see there's forms these lakes. And partly it's because the moraines create high ridges that dam the water, but also partly because these ice sheets are so heavy that they actually deform the crust of the earth beneath them. So the ice sheet weighs so much, it's putting enough pressure on the crust, and the mantle underneath it starts squishing outwards. And so the land is actually lower towards the ice. It tips that water towards where the ice is. In panels 4, 5, and 6, so yeah, I just put 4 in here again. We can see the ice melting away from the area completely, but water is still coming into the lake from the ice. It's just either flowing through the ground sometimes or through stream channels in order to get there. And these stream channels and this water flow help to form two main landforms that we can see today that help us understand where these lakes were. And those are deltas and varves. So I was talking about LiDAR, and this is the LiDAR of the area around Concord, and it shows several of these glacial processes. You've probably all seen LiDAR images before without necessarily realizing them, because they're the basis for most of our maps anymore. Google Earth has LiDAR imaging, and Google Maps. And LiDAR stands for light detection and ranging, and it uses lasers that are sent from an airplane to bounce off of whatever surface they land on, and then using computer models, and then everything that isn't the ground, like vegetation and some human things like moving cars and such are digitally removed so that what is left is a detailed image of the ground surface as it would be if we could strip all of the trees and the human surfaces away. The southeast trend of these hills is because the land there was smeared in the direction that the ice was moving until was deposited and moved around in that same direction. So they look smeared because they were. The ice sheet moved everything heading this way. And then the light teal color is the largest known glacial lake delta in the state. So deltas form as sediments flow from high energy streams and then settle when they reach lower energy bodies of water like lakes. And you can see in this image the current Merrimack River flows through this area. And you can see LiDAR doesn't remove all of the human elements. So these are highways. So here's 393 where it crosses Highway 93. And so this river is looping all around through here. But the delta surface shows us how high the lake used to be. So all of this would have been lake. Uh, and so here on Hazen Drive is where my office is. That means we're on a flat plane of sand that is about 100 feet thick. And is also why the Concord Airport was built up here because it's the flattest place around that isn't floodplain. And this gives you an idea of what these deltas look like inside. This is from a sand quarry in New Hampshire. So the company is using machinery to dig out, and they've taken out literally tons of sand. And I actually just took this photo a few weeks ago near Lake Ossipee. We were there doing field reviews with one of our surficial mappers. And by mapping glacial deposits like deltas, there's a lot of other deposits, eskers, and there's marks like striations, there's moraines, there's a host of other things that show us that these glaciers were here. Surficial geologists can put together a really good idea of where the ice sheet was as it retreated and also where these glacial lakes were. And we figure out when these glacial lakes were by looking at varves. So varves are layers of mud and silt and sand that are deposited annually in lakes. And because each parcel of layers is 1 year, so they're thick in the summer when there's a lot of sediment coming into the lake, and they're thin in the winter when there's a lot less. And they act a lot like tree rings, so they can be counted year by year, and a chronology can be made. And this was started over 100 years ago by a geologist named Antevs and continues today with the New England Varve chronology. So scientists have been finding locations with varves along these glacial lakes, usually taking sediment cores of them. Most of them aren't laid out all pretty like the ones that I showed in the last slide. So they often have to core through the bottoms of modern lakes. But they can count the annual layers and they link sections together. So you can count layers and you'll have usually an especially thick layer one summer or really thin layers all together. You can correlate layers up the lakes. And this gives scientists a very precise idea of when those lakes existed and therefore when the ice sheet retreated. And as you can see, they've done research of lake sediments all over those glacial lakes that I was telling you about, Glacial Lake Hitchcock and Merrimack. And they can form these chronologies that tell us when the ice sheet retreated. And this isn't years before present. This is Varv year. So it's not you have to sort of anchor the Varv years to an absolute year. Um, And scientists have done that, but what they're really looking at is what they call varve years. Okay, so you've probably noticed that I keep talking about these glacial lakes in the past tense, and that a lot of areas that used to be underwater are now dry land. Though some of them stayed big, the Great Lakes are remnants of glacial lakes, but a number of things happened to drain most of them. Partly as the ice melted away to the far north, they simply didn't have the input of water that they'd once had, and they silted up and shrank. Some of them overtopped the sediment that was damming them because of what's called isostatic rebound. I had told you that the crust under the ice sheet had gotten pushed down. Well, as the weight of the ice went away, the ground slowly rose back up a little bit. And so the water um, wasn't ponding in those areas as much. But the most spectacular thing that happened to a lot of them was they burst through the moraines and sediment that was damming them and flooded the areas downstream catastrophically. And we have some records of these catastrophic events where things that should have been covered were scraped all the way to bedrock. So we know that there was a lot of water going through very, very quickly. All right, so getting to the Winnipesaukee area specifically, Glacial Lake New Durham is the name for the lake that preceded Lake Winnipesaukee. It was actually a little bit bigger than Winnipesaukee is now, but not by a whole lot as far as glacial lakes go. The interesting thing about it is that as the ice receded, the lake shifted its drainage pattern. So originally it drained south-southeast along the Cocheco River to the ocean at Portsmouth. But then as the ice front melted further north, it allowed the lake to drain into the Merrimack drainage to the west, as it does now. So it uncovered this lower spillway and started draining this way. And then this image is a LiDAR comparison between, it's kind of the eastern toe of Lake Winnipesaukee and where Glacial Lake New Durham would have been. So you can see some of the same landforms. So here's kind of a valley here. With Glacial Lake New Durham, it would have been underwater. These parts of the lake would have been all together with just this bit here, an island in the middle of Lake New Durham. And Glacial Lake New Durham was the lake level was at about 560 to 600 feet in elevation, which leads me to your quiz question number 2. And this one's kind of an open-ended. Uh, how do you think that scientists know the elevation of Glacial Lake New Durham?
Anybody have? Oh, varves is our first answer.
There we go.
Again with the varves.
So we
Somebody
know
said delta deposits also.
delta deposits. All right. Yeah, so it's because of the delta deposits. So we find the tops of those deposits, and that's how high the lake was. These deltas are really useful for showing what elevation these lakes were at. All right, excellent. So we know a lot of the glacial history of the Winnipesaukee area because it was mapped originally at a relatively coarse scale in the 1960s. And then pieces of that original area were mapped at a finer scale in the 1990s and 2000s. So these are all surficial maps from around Lake Winnipesaukee. And as you can see by Rattlesnake Island in this map here, this map covers part of the area of that bedrock map that I showed earlier that had the Belknap ring dike on it. But notice this doesn't have those same map units. This is a surficial map, so it's focused only on the sands and gravels and sediments that were laid down by the ice sheets, but also the lake and rivers along with it. So uh, this is why we map in different ways. We map bedrock and surficial materials because we can learn different things about an area based on the way that we map it and the type of rock that we're looking at. All right. So I hope that all of this has given you a greater appreciation for geology and what it can teach us about the land around us. And I will put some of these websites in the chat. So we have um, our website for the New Hampshire Geological Survey and also our publication viewer. So if you want to look at some more of these maps, we have a big map viewer where you can zoom in on an area and uh, look at whatever map you're interested in. There's also a really great video about Glacial Lake Hitchcock, that huge lake that goes down the Connecticut River Valley. This video was done, actually uploaded just a couple of months ago by a guy who is actually a science teacher in New Hampshire. But he did a phenomenal job. It looks professionally made. There's some articles about where to see glacial evidence in New Hampshire, although honestly, I'm going to tell you, it's pretty much everywhere. There's a lot to see. I'll also link to the Geological Society of New Hampshire, which is a group of geologists, and we get together and discuss various aspects of the geology of New Hampshire and sort of what's going on. And then the North American Varve Chronology website that I showed earlier that discusses, the timing of these ice sheets and glacial lakes. And then the wonderfully named Friends of the Pleistocene, they're actually redoing their website right now. So I don't have a current website for it. But just so you're aware, there is a whole group of geoscientists that study just, the recent glaciations and various aspects of these, and things like the varves and um, uh, sediments and deltas and all those kind of things. All right, let me do all that and put that in chat.
Thank you so much, Rebecca. I thought that was wonderful and really interesting and insightful.
Yeah, you're
Um,
welcome.
yeah, just a quick reminder for everybody that this will be recorded and uploaded to Lake Winnipesaukee Alliance's YouTube page. I will also drop the link for LWA's website into the chat so that if you are interested in learning more about the work that we do to help protect Lake Winnie and its watershed, you can do so. And I do have another question whenever you're ready, Rebecca, but no rush.
There we go. Yep, okay.
Uh, Someone asked, was there a major outflow break of dammed water from Winnipesaukee?
Not that we're aware of, nothing, catastrophic like we had seen with some of the others. It As far as we're aware, it mostly just changed directions, the where the flow came from. But um, it also, Winnipesaukee isn't that much smaller than Glacial Lake New Durham was that we have evidence for. I mean, a little bit, but probably that was explained enough by the changing flow patterns. So no, Lake Winnipesaukee is actually pretty similar to the lake that would have been there as the ice sheet retreated.
Great, thank you. Does anybody else have any questions, either whether you'd like to put them in the chat or unmute yourself? You are welcome to do so now.
Thanks. You're welcome.
All right. Um, I am not seeing, oh, just a lot of good comments about how great the presentation was.
Yeah, thank you guys.
All right. Well, with that, I guess we could end a little bit early and give everyone a little bit extra time tonight. But thank you all very, very much for joining us. Thank you to Rebecca. This was, like I said, fantastic and very interesting. And for anyone that missed it, again, that recording will be on our YouTube page. So with that, I hope everybody has a great night and thank you so much for coming.